The last section we're going to look at is 7.4. And this is totally different from what we did in 7.3. We're not really going to be using graphing calculators. We're going to be solving equations and getting numbers as answers. We're going to spend probably the next 2 or 3, probably 2 lessons on this kind of stuff. So trig identities are basically a way to take a trig formula and write it a different way. So you guys already know some of them. You know what are called the reciprocal identities. Like if you want to put cotangent in the calculator, there's no button for it. So we could type cotangent a different way. One way is 1 over tangent. That's the reciprocal. Well, there's some other formulas that we're going to use as well. So we're going to look at what all the formulas that we're going to use today are. And then we're going to look at some examples like something like that. And we're going to simplify it. So the reason we usually try to simplify a trig expression, that would tie in with calculus. So if you had to do something with this in calculus, it could be kind of complicated because it's 2 different trig functions multiplied together. If we can somehow get rid of one of them and come up with a formula that still means the same thing as that, that's going to be simpler to work with. So that's kind of the goal, to simplify a formula that has trig in it. Kind of like we did on the first day. We had like sine of inverse tangent, and we simplified it to just algebra. We got rid of all the trig. We're usually not going to be able to get rid of all the trig, not in these. So when you say that cotangent equals 1 over tangent, you're not saying that it only works some of the time. We're saying that that formula works all the time. If you want to know the cotangent of 14, you could do 1 over the tangent of 14. But you could do it for any number you want. Because that is called an identity. So it's a formula that is true for every value that you could plug in. Like Pythagorean theorem, it works all of the time. It doesn't only work if A is 5 and B is 7. You can use Pythagorean theorem with any values. So we've done some identities already. All the reciprocal ones we've done. The tangent and cotangent. Tangent is sine over cosine. Cotangent is cosine over sine. We haven't talked about these yet, so that's why I need to put those up on the board. Okay, so I actually got a table of the identities.
Oh.
So the first 6 there, those are reciprocal.
We've seen this before.
Yep.
Yeah.
Now, there's some repeats here. Okay, these 2 are the same. They're really not different formulas. And the way I usually explain why they're the same thing is think of like this formula, distance equals rate times time. If you solve it for rate, what would it equal?
R equals D over T.
D over T. And if you solve it for T, what would it equal?
T over R.
It would equal D over R. Yeah. So if you look at these 2, all you have to do is switch the R and the T, and you get a different version of the same formula. That's all that's happening in this box. If you switch the cosecant and the sine, you get a different version of the same formula. So they're not really different. So if you flip the cosecant, you get the sine. If you flip the secant, you get the cosine. If you flip the cotangent, you get the tangent. And reversing that, if you flip the sine, you get the cosecant. If you flip cosine, you get secant. And if you flip tangent, you get cotangent. Now, what we haven't really done is apply these to higher powers. So let's think about not just cosecant, but let's think about something like cosecant squared. Well, you could break that down into what? What does cosecant squared mean? when you raise something to the second power.
Times itself.
Times itself. So you really could think of it like this. Cosecant times cosecant. And what's the formula for cosecant? 1 over sine. And what's 1 over sine x times 1 over sine x?
1 over sine x squared.
Yeah, 1 over sine x squared. So cosecant squared is 1 over sine squared. Cosecant cubed would be 1 over sine cubed. These formulas apply to higher powers. Any question on that? Now, quotient identities, we've done these. Tangent is sine over cosine, and cotangent is cosine over sine. And same idea that I mentioned earlier. If you had tangent squared, you can think of it as tangent times tangent, which would mean sine over cosine times another sine over cosine. Well, if you multiply sine over cosine times sine over cosine, what do you get? So if you multiply tangent times tangent, it really just means to do this times itself. Sine over cosine times another sine over cosine. What would that be?
Sine squared over cosine squared.
Yeah, sine squared over cosine squared. So I could say cotangent cubed is cosine cubed over sine cubed. Tangent to the 10th is sine to the 10th over cosine to the 10th. They apply to higher powers. Now, the last group of identities we've never studied. These do not apply to higher powers. They only apply to exactly what you're seeing. And here's the first Pythagorean identity. It says sine squared plus cosine squared equals 1. So if you take an angle, let's just try it. Yeah, you could do it in degrees or radians. I'll just do it in degrees. Let's pick 23 degrees. So take the sine of 23 degrees, square it. Take the cosine of 23 degrees, square it, add them up, and you get 1. It wouldn't have mattered what angle I put in right there. I would have gotten 1 no matter what. And they call it a Pythagorean identity because it has these exponents of 2. So it kind of looks a little bit like what you see in Pythagorean theorem with the exponents. Okay. Any question on the first Pythagorean identity? There's 3 of them. But even if you don't remember the other 2, if you remember this one, you can figure out the other 2. I want to divide everything there by the same thing. Let's take this equation. And if I divide everything by the same thing, and I do it correctly, is my equation still true?
Yeah.
Yeah. Let's divide everything by sine squared. What's sine squared divided by sine squared? 1. This one we kind of just talked about. Think of what cosine over sine is.
Secant? No, cotangent. Sorry.
Cotangent squared. And what is 1? Think of what 1 divided by sine is, and then just apply this to the second power. Cosecant squared. That's another Pythagorean identity. 1 plus cotangent squared equals cosecant squared. It's not the one I had next. It's the last one. This one I didn't prove to you how to get that one from the first one, but what do you think you would do to the first one to get? Yeah, if you divide everything by cosine squared, you could get that one. Okay.
Alright, which was the one that we ended up with
I did this last one. 1 plus cotangent squared equals cosecant squared. I didn't remember which one I had next. It's the same idea. So these are called fundamental identities. I don't know if it says that. Yeah, fundamental trig identities. They're the identities that, if you're going to memorize identities to use, these are the ones that most people would know. How many? There's a ton more. Right? How many more? Hundreds. Tons of identities. But the Pythagorean, the quotient, and the reciprocal, those are like the real basic ones that you use to figure out all the other ones. So there's really, I think, about 11. So there's 3 reciprocals because there's repeats. Well, actually, if you count it all 6 separate, let's say there's 6 there, 2 there, and then 3. That's how I get 11. But really, there's only 3, 2, and 3. So there's 8 different formulas to remember. And I don't count applying it to a higher power as a different formula, because then it'd be infinitely many. Now, the other thing you can do with the Pythagorean identities is you can rearrange them. So instead of having 1 by itself, we could have something like this. All I did was subtract sine squared to the other side. So I don't consider this a different formula. It's just a rearranging of one that we already had. If you count all the rearrangements, then there's tons of them. Okay. Any question on that idea of rearranging that? So that's pretty much it. Those are the formulas that we're going to use.
We're not using the calculator for any of this.
Nope. Okay, so we just went through all that. If you look on the chapter 7 book online, and you go to page 403, I think it has that exact chart that I just showed you. That's where I got it. Okay, I already mentioned why we would simplify identities. And there's a few different approaches, okay, to when you're trying to simplify an identity. One approach that we use quite a bit is to change everything in the problem to sines and cosines. So if you see something that's not a sine or a cosine, look up one of the identities and change it to sine and cosine. Now, I'm not saying you're going to do that every single, 100% of the time. There might be a time where it's easier to not do that. It depends on the problem. But a good amount of the time, this is a good idea to try. Okay? Change everything to sines and cosines.
We're going to try that.
Yeah, the tricks in general are changing everything to sines and cosines, finding common denominators, and multiplying by conjugates. Those are the 3 big things that we do to try to simplify identities.
We're just focusing on this one for today?
We're focusing on this one right now. But we're gonna do the other ones today too. Okay, so here's one. Cotangent divided by cosecant. So let's try the first technique, which is to take whatever there you have and change it into sines and cosines. And the hope is when we do it, stuff cancels out. Let's start with cotangent. What can you substitute in for cotangent? Okay, so cosine over sine. The angle, or the Greek letter, or the English letter that you use in the trig function, that doesn't really matter. It's just your variable. And what can we change cosecant to? Okay, 1 over sine. So now, what would happen there when you divide those?
Sine cancels out.
The sines would cancel out. And what are you left with?
Cosine.
Just cosine. Yeah. Okay, so that would be considered a very, very neat, very clean identity. It's simplified quickly. There really wasn't a lot of different ways you could even think about doing it. And you got a very nice answer.
Alright, so we should... Alright, Should we have to chart all the identities down somewhere? Just so it's easier?
I would make sure you have that chart written down that I have on the board. Yeah. And eventually, really, you need to know that chart.
Yeah.
You know, if you work with the identities enough, you're going to start to know the identities. And you already know all the reciprocal ones. And the tangent and cotangent ones. So really, I think the only new ones are the Pythagorean ones. And even for that, if you just remember the first one, you can figure out the other two if you have to. So, there really isn't too much new information. Questions on that? Okay, let's try this one. This one about the same type of difficulty. The last one and this one would be considered pretty easy identities. All right, what could we do with cosecant? We could make that 1 over sine. And what about tangent? Right. You might say, well, what about 1 over cotangent? Well, the goal here was to try to change to sines and cosines. I'm not saying 1 over cotangent is a bad idea all the time, but it's a bad idea this time. And when you multiply straight across, what happens? Sines cancel out, and we're left with 1 over cosine. And at this step, you might wonder, well, should I keep going? What should I do? I would say if you can write something not as a fraction, that's simpler than having a fraction. That's just secant.
Even if it's like reverting back from the sine and cosine.
Yeah, that's okay. Because I would say that this is simpler because it's not a fraction. And sometimes we're going to do some problems that don't say simplify. They say verify. So with verify, it's actually easier because they tell you what to start with. They tell you what you're going to get as an answer. And then all you have to do is figure out how to get from one side to the other. So you know when you're done. In a simplify problem, it's a little bit more vague. Simplify basically means keep going till you think you're done. Any question on that one? So in the first two examples, we were simplifying an identity. Okay, simplifying it, hopefully one of the trig functions disappears and it gets simpler than what you started with. This one's a little different. This one says show that this is not equal to that. Showing something is not equal sometimes can be a lot easier than showing like what we had to do in the first two problems. How could you show that what's on the left does not equal what's on the right? Yeah?
Simplify the left side until it's something that definitely cannot be cosine.
Okay, so you could try simplifying the left-hand side until it's very clear that it's not cosine. Or what else could you do? Because when you want to show that something is true, you have to do it that way. You have to use trig identities and simplify it till you get the same thing on the left and on the right. But to show something is not true, you can do that a lot easier. Yep.
Just show that it's something else.
Okay, by doing what? Yeah? Yes, find a counterexample. So when you're trying to prove that something is not true, all you have to do is find a counterexample. Because if you can find one place that this doesn't work, then you've proven what's on the left does not equal what's on the right. Now, when you do a counterexample, you want to pick a value that doesn't seem to be special. So I would not pick 0. I wouldn't pick like 90 or 180 or 270. I would plug in one of those nice angles. Because you can see, if you graph this.
Oh, wait, like actually just plug in numbers?
Yep.
Show the mark, I see.
If you graph 1 plus sine squared divided by cosine squared. I think I put an extra set of parentheses. Actually,
If you need it.
Yeah, you did.
I should have closed it here. And then I probably don't need it here. Okay, that should be fine. And then if you graph cosine, let's see what that looks like.
It's just gonna show that they don't do this.
Well, it's going to show that they look different, but they are the same for some values. So if you happen to pick 0, which I said not to, you would get the same answer on the left and on the right. If you plug 0 in on the left, you're going to get 1. If you plug 0 in on the right, you're going to get 1. That's not a good counterexample. You need to find a value where they're different. So plug in something like 90 degrees. That would be okay. Or 92 degrees. Do something like that. That would show that they're not true. Or if you're doing radians, don't do pi. Do like 3. Do something a little off from pi. And if you plug it in on the left and on the right, you'll see you won't get the same answer because they're not the same graph. So questions on the idea of showing that something is not true?
So either plug the equation, so the answer is just plug in a number.
Find a counterexample. Yep. Yes.
So would you write your answer as if theta is equal to this?
Yeah. I'd say let theta equal 2.5. Pick a random number. If I plug it in on the left, I get, I just use the table and figure it out. Second table, 2.5. If I plug in 2.5 on the left, I get 1.004. If I plug it in on the right, I get 0.999. And those two values are not equal, which proves what's on the left does not equal what's on the right. But again, a bad one to pick would be 0, because if you plug 0 in, well, now it makes it look like what's on the left is the same as what's on the right. And in that case, it is. But in most cases, it isn't. Question on that? So verify is the other type of problem I mentioned to you. It's a little easier than simplify because you know what to start with, you know what to end with. You just have to figure out how to get from the more complicated stuff to the simpler stuff. You just have to figure out how to do it. So the approach that we're usually going to use when we have to verify an identity is start with the side that's more complicated and do what you can to simplify it. Don't do it in reverse. Don't take something that looks simple and try to do stuff to it to make it more complicated. That's going to be confusing. So start with the more complicated side and turn it into the simpler side. If you can't tell which side is more complicated quickly, then it probably doesn't matter which side you start with. Now, another approach is to try to do both sides at the same time. Do a little bit on the left, do a little bit on the right, till you finally get them to be equal. I think we'll probably just stick with doing it this way.
Like, that seems like it's significantly more work.
Yeah, it depends. If both sides are pretty complicated, you might do a little bit to one side, do a little bit to the other side, but we're not really going to have problems where both sides look complicated. One side looks complicated, one side doesn't. So it just depends on the problem. So we're not going to do that. All right, so second trick that is going to come up, besides changing everything to sine and cosine, is finding a common denominator. This only applies when you have problems that have different fractions, different denominators. We haven't done one yet where this would apply. Common denominator means usually addition or subtraction has to be involved. and it has to be addition and subtraction of fractions. In the second problem we did, it was multiplication of fractions. Common denominators never comes up when you multiply. Common denominators also doesn't come up when you divide. So we haven't done a problem where this trick would be helpful yet. And if we look at this one right away, I wouldn't think common denominators is coming up here because I don't have any denominators at all. But as we start to do the problem, we may change things into fractions, and then all of a sudden we do have denominators. Okay, so keep that in mind. Okay, you've got a little bit of a choice at what you could do first here. What property do you think is going to come up here? It's a pretty common property, yeah? Yep, you need to distribute the sign. So you can either distribute it the way it is now, and then change to sines and cosines after, or you could change to sines and cosines now. Let's distribute it the way it is. So when we distribute, there's not really a lot we can do with sine times cotangent. We're just going to leave it sine times cotangent. And what's my next?
That's not sine of cotangent.
No, that's sine times cotangent. And what would my next term be? Sine times tangent. Okay. Now we don't have any other choice at this step. We have to do something. What do we have to do now? Yep.
You could do sine times cotangent, and then it would cancel out the sine of cosine.
How could we make that easier for people to see?
Sine over 1 times cosine over sine.
Sine over 1 times cosine over sine. Okay, let's keep doing that kind of same idea.
Then you could do sine over 1
times sine over cosine. And what did you say is going to happen?
Why is it cosine over sine?
That's the identity for cotangent.
Oh, it's cosine. I had it as cosine up on the top.
Sines cancel out.
Which ones?
Left side of the addition.
Yes. You can cancel if you have the same trig function in the top and the bottom to a multiplication sign. You cannot cancel trig functions in the top and the bottom across an addition sign. You cannot do that. That's multiplication, so that's okay to do. Okay, so we get cosine over 1 plus sine squared over cosine. Okay, so we've changed everything to sines and cosines. So that trick is done. What's another strategy I gave you for solving something like this? Common denominator. The common denominator, easiest way to find it is it's the product of the two denominators you already have. So what's my common denominator here? Cosine. The second fraction already has it. The first one doesn't. What would I need to multiply? And it has to be the same thing in the top and in the bottom. Cosine. Okay, so that's going to give me a common denominator of cosine. And what's that going to give me in the top?
Sine squared.
Plus sine squared. And now here you have to recognize something. There's something there that simplifies. Yep.
The numerator will simplify to 1.
The entire numerator turns into a 1. That's the first trig identity I gave you. Sine squared plus cosine squared equals 1. So that entire thing turns into that. Which now, we can simplify to secant.
So that whole thing is just equal to secant.
So we started out with something that was pretty complicated. It had 3 different trig functions with a distributive property, and the whole thing reduced to just a single trig function, secant. It's going to be way easier to work with secant than it is to work with the original model. Any question on that one? And again, I might make these look easy. Some of them are harder, but the ones that we're doing, they're going to follow one of the 3 strategies every time. Sines and cosines, common denominator, and conjugate, which we haven't done.
How do you tell which one is
Experience.
Oh, okay.
That's it. Alright, so when I look at this one right away, I haven't done this in over a year. I don't remember how to do it. So I definitely can tell which side is more complicated, which would be the what? The right. So we're not going to do anything to the left-hand side for this entire problem. We are going to work with the right-hand side. And when I'm done working with it, my goal is to get sine. If I do, then I've proven what's on the left equals what's on the right. If you start doing a problem and you notice it's getting worse and worse and worse and it's just not getting anywhere, then step back and try something else. Okay, because there's lots of different ways to sometimes prove an identity. Not that you have to find the easiest way, but you certainly don't want to keep trying a really hard way if it's not getting anywhere.
Sorry, what's the RHS words?
Right hand side.
Right hand. Okay. Any suggestions what we try to do first here?
Change everything to sine.
Alright, I am going to change to sines and cosines. I'm not going to do it to the top yet. I probably will end up doing it anyway. But I just want to do it in the bottom because I see 2 things here. And I know when I change to sines and cosines, I'm going to get fractions. Then I'm going to be able to do common denominators. And then I'm hoping something nice happens. I might still have to change the top to 1 over cosine eventually. But let's just leave it for now. So secant over sine over cosine plus cosine over sine. What's my common denominator for the bottom? Yeah.
Oh, sorry, sine times cosine.
It's going to be sine times cosine. Actually, I shouldn't put that there. I should. Let me put the top first. And then the bottom is going to be more like down there. Sine times cosine. Okay, let's figure out what's going to be in the top. Each one of these fractions has to be multiplied by something to get the common denominator. The first fraction only has a cosine. What is it missing to have the common denominator?
Sine.
It's missing the sine. So we're going to multiply by sine over sine. Anytime I get sine squared, I like that because I'm hoping I get a cosine squared somewhere else. And sine squared equals cosine squared turns into a 1. So that's kind of what my head is thinking about right now. Okay. In the second fraction, we have the sine in the bottom. What are we missing to have the common denominator? Cosine. Now, if I do that out, what's sine times sine?
Sine squared.
Sine squared. And cosine times cosine?
Cosine squared.
So that's great. So now I have secant. Just think of it like this, secant over 1. Just because when I have a fraction, to me, sometimes it seems weird to have like 3 parts. I'd rather just have 4. a numerator and denominator in the top, and a numerator and denominator in the bottom. Okay, what's sine squared plus cosine squared? 1.
Wait, where'd you get 2 ones? Oh,
I just wrote secant. You'll see why I did that in a second, but you'll see. I just put secant over 1. Now we have a fraction divided by another fraction. How do we simplify when you divide two fractions? Can you explain more? Multiply what by the reciprocal? The numerator. So keep the numerator the same and multiply by the denominator flipped. So sine times cosine over 1. Now at this point I think I am going to change secant to sine and cosines because that's going to make something nice happen. One of the reasons I didn't change it earlier is because when I change it, it's going to turn into a fraction. And I didn't want to have to keep writing a fraction for secant for this entire problem. So what does secant turn into? It turns into 1 over cosine. Times sine times cosine over 1.
Basically, it's just
So what cancels out there?
the cosines.
The cosines. And what did that entire thing turn into? Sine.
no way those will
Now this was a verify. So we can go back and there was something we were supposed to get. What does it say we were supposed to get? Sine. That's exactly what we should have gotten. So at this point we know we're done now because we turned the right hand side into the left hand side. And that's probably as simple as you could do that one.
Well, that's the simplest way.
I don't know if there is. I mean, maybe there is. I don't know. You'd have to play with it and see, but that might be as simple as it gets. Some identities, to prove them, can be pages. I mean, just pages. The longest one we do will probably be about 40 pages.
What are we actually saying?
I'm just
Are there any topics that are actually going to be like that one?
not that we do. I mean, we might get a little harder than this, but it's pretty. You know, that's like a medium one.
But you knew exactly what to do and you had to figure it out as you
So you only have certain things you can try, right? When you get to a problem, the only tricks I've given you are the sines and cosines, common denominators, and there's one other trick.
Are we going to learn that?
Yeah. If you're not going to run into an identity that doesn't follow one of the paths I've already described how to do. Because there are other ways to solve identities besides what I'm teaching you, but every problem I give you is going to fall into one of those 3 things. Every time. Okay, so the last trick. We've used this before with complex numbers. When we don't want to leave an I in the bottom of a fraction, we multiply the top and the bottom by the conjugate. What's the conjugate of 3 minus 4i? 3 plus 4i. So the way you know to use conjugates in a problem is you're usually going to see either a numerator or a denominator that has like a number plus or minus a trig function. When I look at that problem, I see conjugates all over the place. I see a trig function, and then a 1, and then a plus or a minus. I didn't have anything that looked like that in any other problem.
Okay, so our conjugate problems can be easy to spot.
Yeah, they're pretty, because like this is not a trig function plus or minus a number, right? This is not a trig function plus or minus a number. That's a distributive property. It doesn't look anything like a conjugate problem. That's a conjugate problem. That is definitely a conjugate problem. I can tell quickly. It's a trig function with a plus or a minus and then a number. It doesn't have to be a 1, but in this case it's a 1. Now the other thing about conjugate problems is neither side looks that more complicated or simple than the other. So in that kind of thinking, it's not really going to simplify nicely.
Sorry, what was the rule again?
So the conjugate is when you change the sign of what's between the two terms. If it's a plus, you make it a minus. If it's a minus, you make it a plus. Since in this problem, both sides look like they're about the same level of difficulty, it does not matter what side you start with. So you can pick. Do you want to try to work with the left side or work with the right side? The right side? Okay. So when we're done, the goal is to end up with the left side. Okay, so we're going to forget about the left side for now. That's what we need to get as our answer. And we're going to work with the right-hand side. So if you're not sure what to do, run through everything that I've explained so far. Should we try changing to sines and cosines? It already is. Maybe sines and cosines will come up later, but not now. Should we try a common denominator? No, we already have a common denominator. There's only one fraction in this whole thing. So the only trick you have left is the conjugate. Okay. What has a conjugate here? The top or the bottom? It's the top. You're not looking at the bottom. That's a single term. Conjugate, you're looking for two terms. What's the conjugate of 1 plus sign? 1 minus sign. Now the top, we are going to have to FOIL that out. That's a binomial times a binomial. But in the bottom, I'm not going to FOIL or distribute cosine to the 1 and cosine to the negative sign. The reason I'm not going to do that is because I already know this cosine is going to cancel out. How do I know that? Well, I'm kind of hoping it cancels out because I'm looking at the left-hand side, which is my answer, and there's no cosine in the bottom. So this cosine better disappear somehow. So we're just going to leave the cosine times 1 minus sign. The rule generally is when you have conjugates, always FOIL the conjugates first. Leave everything else in the problem the same. Because 9 times out of 10, if you FOIL these conjugates together, something is going to cancel out, eliminating a step you might have been thinking of doing. Okay, so let's FOIL. So 1 times 1 gives me 1. 1 times negative sign. And 1 times positive sign. So negative sign, positive sign. Those are gone. Positive sign times negative sign. Well, what's a positive times a negative?
Negative times squared. Negative sign squared.
Negative sign squared. Now, 1 minus sine squared kind of looks like something we've talked about. What does that kind of look like?
Cosine squared is 1 minus sine squared.
Right, it's the first Pythagorean identity. It's not written exactly the way I gave it to you. Sine squared plus cosine squared equals 1. Rearrange it so you have 1 minus sine squared on one side. So you have to subtract and subtract. So what does 1 minus sine squared turn into? It turns into cosine squared. So in the numerator, you can replace that with cosine squared. Now, what you have right there is basically this. 5 squared over 5 times something else. If you were trying to simplify that, you'd look at the top, look at the bottom, and you try to identify if you have any common factors. And if you didn't know what squared meant, you could write it like that. What cancels out here in the 5 times 5 over 5 times 3?
The 5.
The 5s. You had 2 copies of 5 in the top, you had one copy of 5 in the bottom, so you can cancel one copy of 5 from the top and the bottom. What does the top and the bottom have in common in this one? Cosine. How many copies of cosine in the top?
2.
And in the bottom? 1. So you can cancel 1 from the top, 1 from the bottom, and look at what you get. You get cosine over 1 minus sine. Which, if you go back up, that's exactly what the left-hand side is.
That is. Oh, neat.
So it doesn't really simplify and like have a lot of stuff cancel out like some of the other ones. But the pattern when you have conjugates is exactly the same. Had you chosen the left-hand side, it wouldn't have been any easier or harder. It would have been the exact same amount of steps. Okay, any question on that? All right, so we've seen every type of problem. This one is pretty much the same as the last one, so I think I'm going to skip it. I'd probably just start with the right side and multiply top and bottom by cosecant minus 1. And when you FOIL out the conjugates, you're going to get the trig identity we talked about. I think I'm just trying to find one that looks hard to me. Alright, let's try this one. I don't know how to do this one. I do remember doing it before, and one way we can do it was really hard, and then there was another way that made it really easy. Just can't remember the really easy way off the top of my head. Oh, there's some on my work though.
Only half the argument is not.
I mean, you solved it eventually.
Yeah, I did.
You got.
I think I would work with the right hand side. I know it looks a little more complicated because it has 4 different terms versus the right side has 3. And when I see tangent squared minus 1, hoping that we could get an identity somewhere maybe that comes up. I don't know. Alright, I guess we'll just try the right hand side. I don't know. Let's try the right hand side and see what happens. Okay, so if we're going to work with the right hand side, what would we do first? Oh, wait a minute.
Yeah, that would be easier because there's the thing that turns into +1 and then just be secant squared.
Tan squared minus
Yeah.
1, just secant squared.
Yeah.
Which is
So then you could cancel.
Well, 1 plus tangent squared is secant squared.
Yeah. But you use it.
so then tan squared minus 1.
So tangent squared minus 1 is nothing.
Oh.
Yeah, tangent squared minus 1 is nothing.
Then
This would have to be a plus sign. If that was a plus sign, then this whole problem would be done in one step.
Oh wait, because those are all just one.
All right, I have an idea. So I'm looking at these two things. I'm looking at that. I'm looking at that. And I'm wondering if there's a way that I can force the top of the right to look like what's on the left. So let's focus in even more on just this and that. If you wanted to turn tangent into tangent squared, which is what we want to do, what would you have to do to tangent?
Multiply it by the
Multiply it by tangent. So let's try that. Let's try multiplying, but you can't just do it here. You have to do it to all of them. So let's multiply them all by tangent and see what happens. So I'm going to copy the whole thing down first. over tangent plus cotangent. And I'm going to multiply, or I'm going to distribute tangent to the top, and I'm going to do it to the bottom. And the whole point to me doing that is to try to make this look like that. I don't know what it's going to do to everything else. I have no idea. But I do know if I multiply it by tangent, it is going to make the upper left exactly the same in both. Hopefully it makes the upper right the same in both, bottom the same in both, and everything just works out nice. Let's see. So what's tangent times tangent? Tangent squared. And tangent and cotangent, or what's the connection between them? They're reciprocals. And anytime you multiply two things that are reciprocals, like say 5 and 1 over 5, what do you get? 1. So by multiplying the top by tangent on the right, we made it look exactly like what's on the left already. Now the bottom is what I'm not sure exactly what's going to happen here. Oh, yes, I know. Oh, it's great. Yeah, we're good. I get excited. So distribute tangent in the bottom. What's tangent times tangent? Tangent squared. What's tangent times cotangent? Plus 1. And tangent squared plus 1, I just had that written down. This is a trig identity, and it turns into secant squared, and we're done the whole problem in like 2 steps. My other thought was going to be to take the right-hand side and change it into sines and cosines. And I remember we did it that way before in another class, and it works. But instead of being 2 steps, it turns into like 8 or 9 steps. It gets really bad.
Wait, that's only considered 2 steps?
Well, yeah, so the 2 steps were multiply top and bottom by tangent. So that's the first step. And then the second step was changing this denominator to secant squared using a Pythagorean identity. Yep, that was it. So a lot of times there is an easy way. That's why I looked at it for like a minute or so to try to figure out an easier way. Probably not something you would have thought of on your own at first, to try to make this look like this by multiplying everything by tangent. But now that you've seen that trick, that may come up in another problem. You might think, oh yeah, let me try that thing I did before. Any question on that one? That one is I would say that's probably a conjugate, because there's trig functions plus 1s and minus 1s all over the place. So I'm not really guessing where to start with that. It's going to be a conjugate problem. And that's the calculator. So the point with the calculator is you can't use a calculator to prove an identity. So if you had, like, let's say you put this in y1, and then you put this in y2, and they look like they're the same. Well, that doesn't prove they're the same. When you would want to graph it would be if they gave you a problem that said, like, verify if possible. So if it said if possible, now they might be giving me a problem that's not even true. So I don't want to spend all day trying to work with this if I'm never going to get an answer that even works. So if it said verify if possible, I would take and put that in y1. I would put that in y2. And I would see, do they look the same? And if they look the same on the calculator, then they probably are the same. And then it's worth my time to try to prove it. If I graph one of them in y1 and it looks like this, and then I put one in y2 and it looks like that, then there's no question. These are 2 totally different things. They're not the same at all. And I would just give a counterexample and say, that's impossible, because here's my counterexample. Any question on that idea?
So some of these aren't. Wait, what if we? Okay,
But the ones I give you are going to be provable.
Okay.
I'm not going to be giving you ones that say verify if possible. They're all going to be true. So you're not really going to have to use the calculator to check it. Yeah, I had just lots of practice examples. There's nothing new in any of these problems that we haven't already talked about. So the trig identities, they really they take a little bit of practice to get used to.
Just do Monday.
So this would be due when we come back on Monday. If you get stuck with an identity, chances are staring at it for 15 more minutes isn't going to really help. If you're stuck on it, you might just be stuck. So my advice would be try another problem, and maybe something will come up in another problem, and you're like, oh, I can try that in this problem.